Hey, welcome, welcome, welcome. Today we are taking a look at carbohydrates. So unit 4.2, we're looking at pencil working here. And we're going to need a new pencil right off the bat. All right, fantastic. Here we go. Hopefully this one has some better luck. So today we're looking at carbohydrates. These are often also called sugars to the layman. You'll see, give you a lot of examples of carbohydrates today, and you'll see that a lot of them are in one form or another a sugar that we are aware of. So this is our fourth macromolecule. We started the year working with lipids, with the phospholipids and triglycerides, mainly. Then we moved into nucleic acids. But the last two units really focused on nucleic acids, and then recently we have been in proteins. This is the fourth of the main macromolecules, 4 of 4. So hopefully we are all comfortable with the fact that they have monomer units. Nucleic acids have the nucleotide, proteins have the amino acid, and carbohydrates have the monosaccharide. So one monosaccharide, I think there's only one S in there. I'm sorry about that. Monosaccharide. Might be two C's here, though. We'll have to check the spelling. So monosaccharides. Monosaccharides. Yeah, it is two C's. Thanks. Monosaccharides. Mono means one, Greek for one. Saccharide is Greek for sugar. Just put a little saccharide in your coffee. So one sugar. Now, unlike proteins and unlike nucleic acids, monosaccharides by themselves can be a monomer unit. Again, that's different than nucleic acids, different than proteins. If I give you one amino acid, it is not a protein. If I give you one nucleotide, it is not a nucleic acid. You need to have these long chains of them in order to make the macromolecule. But with carbohydrates, you can have just one monomer unit, just one monosaccharide, and it is considered a carbohydrate. Take a look at some examples in just a second. First, you have probably seen by this point in the year that we pretty much always use a hexagon to represent a carbohydrate. There's a very good reason for that, and that is because it is C6H12O6. All monomer units, all monosaccharides have the same formula, C6H12O6. And the reason why we use a hexagon is because those 6 corners represent the 6 carbons. And you might be saying, wait a minute, what about that O? And you're absolutely right. One of those corners is an O, and that's because there is a carbon flag kind of flying off to the side here. And that O is just kind of structurally what links the entire thing together into a ring. So there's carbon number 6 kind of floating around up there. I didn't draw the remainder of the O's and H's. They're on there. In fact, you'll probably see it in your homework tonight. They are on there, the O's and the H's. But the carbons, they're the important part. So we'll put those guys around like that. All right, so some important monosaccharides. You're probably aware of this first one, glucose. This is our main energy source. Talk a whole lot more about that in a couple of chapters when we get to photosynthesis and cellular respiration, but this is our main energy source. Now this, again, the hexagon, I'm gonna kind of color it a shade of blue here. You are welcome to color it as well, or if you prefer. Just write the letter G on that for glucose. Next up, another pretty common monosaccharide, fructose, which is the sugar found in fruits. Fructose. Oops. All right, so we also have fructose. So fructose is found in fruits. It's pretty easy to remember, FR and FR. Fructose is kind of the oddball. Fructose is a pentagon. Most of our monomer units are going to be hexagons. Fructose is a pentagon, so a little different there. Oddball out. Now, in case you're wondering, this isn't, again, terribly important. His structure is just a little bit different. He's got the O on top, and then a chain of 4 C's that go around him. And you have to saying, well, wait a minute, what about the 6 C's? Well, he's got the one flag here, just like these guys. And he's got a second flag over on this side. Like, wavy arms here. There's wavy arms. That's fructose. Just a little oddball because he's only got 4 carbons, 5 total atoms in the ring there. All right, finally, the third common monosaccharide, galactose, which is a sugar found in milk. Galactose is almost identical to glucose. It's also a hexagon shape. It looks very much the same. In fact, in your homework tonight, you guys will get some practice identifying what the differences actually are, and they are tough. I think I even had to highlight the differences so that you would recognize them, because the difference between glucose and galactose is very, very small. All right, so there's our 3 main monosaccharides. This next step should look somewhat familiar to you. We got 2 monosaccharides here. And we're going to combine them to form what we call a disaccharide. So disaccharide, Greek for 2 is di, and then saccharide, 2 sugars. And there we go. We have combined 2 of our saccharides, 2 of our monosaccharides to make a disaccharide. And what came out? Let's take a quick look here. We have an OH and an OH. We now just have an O connecting them. So what came out is both H's and one of the O's. An H2O. We have seen this before. We saw this with lipids. We saw this with nucleic acids. When we bound that those sugars to those phosphates, a water came out. And we saw this last week with proteins. When we bound amino acids, when we have a peptide bond, water comes out. It is a dehydration synthesis. Exclamation point. All of our all of our macromolecules are all linked together through what's called a dehydration synthesis, which has water coming out. Dehydration synthesis. Just like the bond for proteins between amino acids has a special name, a peptide bond, this bond here also has a special name. And there's called a glycosidic linkage. The glycosidic linkage is the bond that links 2 saccharides, 2 monosaccharides to make a disaccharide. Between those 2, in fact, if we continue to make them longer, we will in just a few minutes here, We'll see there are a lot of glycosidic linkages. Some common disaccharides. First up, we have maltose, often called malt sugar. So there's another sugar. Malt sugar is made up of, well, let's see if you can figure out the color coding I'm using here. Two hexagons, light blue, two glucose together make up maltose. So malt sugar, we found that in cereal and pasta and potatoes, a lot of malt sugar in those boys. Another common one is sucrose. This is commonly table sugar. There's our blue glucose, and he is going to be bound to, well, if you remember the colors, awesome, but otherwise it should be the shape that helps you on this one. He is bound to the pentagon. The pentagon was fructose. So a glucose and a fructose make up sucrose. And then finally, the third common disaccharide is lactose, which is a milk sugar. And this one, you might have guessed, is going to contain galactose. It has one glucose. And one, there's that green galactose, which makes sense. You'd expect to find the sugar found in milk sugar as well. And there it is. A glucose and a galactose makes a lactose. Oh, so don't stop at disaccharides, though. They can get much, much larger. This five monosaccharide one doesn't even do it justice. But once you get large chains, they're called polysaccharides. And these polysaccharides might be millions and millions and millions of chains long. So really doesn't do it justice to draw just a few of them. But that's the polysaccharide. That's your large one. And I thought I could give you guys some examples, A, B, C, like starch and cellulose and glycogen. That's one that humans make, animals make. But I'm interested in this. Someday I want to get more into this. Want to delve a little deeper. And we might this year. Might have to wait till next year. But I want to introduce it here now. Okay, so I'm going to draw another chain here, another polysaccharide chain. And I'm going to draw another one down below it. All right, so we've got two chains here, and these are actually chains of cellulose. So that's the polysaccharide we're looking at. And then I'm going to kind of lash them together. almost like a rope-like substance. And these are actually polypeptides called pectin. So these are polypeptides, not full proteins, just links of amino acids. I don't think they're technically a full protein yet, but they're chains of amino acids that act like rope. To kind of tie together all the cellulose. And what are we looking at here? A plant cell wall. This is what a plant cell wall looks like. We've got lots of strands of cellulose, and they're kind of tied together with pectin. And what is pectin? It's a polysaccharide or polypeptide, excuse me, polypeptide that binds cellulose like rope, kind of ties it together. All right, Richardson, where are we going with this? Well, you're going to love this, but just two more. Polysaccharide chains. Coming off these polysaccharide chains are going to be another polypeptide, but they're going to behave just a little bit differently. So what we've drawn here is what's known as peptidoglycan. So peptidoglycan is kind of a combination, peptid, hopefully we're recognizing like polypeptides, and glycan, which is really basically our glucose molecules. So we've got this combination of glucose and polypeptides. And they're a little bit different than the plant cell wall. So the plant cell wall kind of uses pectin like rope to kind of keep everything tied together. The peptidoglycan uses their polypeptides as kind of almost like chains with hooks on them, and they kind of hook together. It's a lot like how Velcro works. Have you ever seen Velcro? Velcro is a bunch of metal pieces that are kind of bent, and then you take another piece of Velcro, and those pieces kind of latch on together. Well, that's very similar to what we have going on here. This is bacteria cell wall. So we've got plant cell walls and we've got bacteria cell walls. And we have a wonderful, wonderful drug. I mean, this has really changed the world, the way the world works, how medicine works. Penicillin penicillin kills bacteria by preventing them from making peptidoglycan. So penicillin is this wonder drug that's really only been around. We discovered it in the 1920s, Alexander Fleming, but we've really only been able to mass produce it since about the 1940s or 50s. It hasn't been that long, and it's really changed the world. 100 years ago, if you got a cut on your arm, there's a good chance you just lose your whole arm. That's what we do. We cut off your arm. We had no way to stop bacterial infections. So if you had anything that, any kind of disease and kind of cut any way that the bacteria got into you, one of our forms of medicine, cut off that body part. Don't let the disease spread to the rest of your body. So kind of barbaric almost, but hey, it kept people alive, and that's what we had. And then 1940s, well, 1920s, it's discovered as this, again, a wonder drug that is able to kill bacteria. And the way that it does that is it prevents them from building the carbohydrate protein that holds together their cell walls. When their cell walls degrade, they can't hold the cell together, the cell bursts, and voila, we found a way to treat bacteria without just cutting off your whole arm. So really pretty cool. I hope we are able to get back to this year. We'll see, but that's why penicillin works on bacteria, but doesn't work on plants. Penicillin does not kill plant cells because they have a completely different structure to their cells. They have pectin and cellulose as opposed to peptidoglycan. So wanted to throw that out there again. There's gonna be a day where I'm like, remember when? And this is what I'm going to be referring to. I hope we get to it today. Sorry, this year, not today. Today, we are done. So I'll see you next time. Signing off to Lynn.